All right, welcome to the second part of the chapter 2021 lecture. This is Birth of Stars, and in this part, we're going to look at a couple different subjects. We're going to look at the life of stars, and we're going to also look at extrasolar planets and how we detect some of these things. And the reason that may seem like a unrelated topic, but as you know from the solar nebula theory, that planets and stars are sort of born together. So it is really tied to the birth of stars, right? so um, now I want to recap what we talked about in the last video lecture because it's just really important to remember all the details about the birth of stars. So this slide here is a really nice sort of summary of everything. So the sentence that's at the top here, this is if you had to describe star formation in a sentence, this is the sentence. Stars are born from the collapse of a dark, cold interstellar cloud. So that's in a single sentence. There it is. That's star formation. And we talked about a couple mechanisms to do this, right? How do you initiate the collapse? Well, you can either have a massive star explode and push on these clouds, and that can initiate the trigger for the star formation to begin. You could also have really massive stars nearby that have very intense starlight, and they can push on the interstellar clouds, and that can cause the star formation to occur. Now, there's something really simple about star formation. It's kind of the same way you could talk about, human formation is that, just like every human, stars go through sort of the same steps in the process of forming into a star. So regardless of the mass of the star, regardless of whatever forms out of it, they always go through these same stages. So there is some collapse of an interstellar cloud. And then that collapse, what's going to happen is parts of the cloud will fragment into pieces. Those pieces are going to start to shrink down and start to gather up material from their surroundings. And that's what we refer to as the protostar stage. Typically, that stuff's embedded in the nebulas. We don't usually see these kind of stars, although we did mention the Herbig-Haro objects because sometimes there are visual signs of these things forming. At some point, the objects will emerge out of the nebula they formed in, and they will start to resemble stars in pictures, and those are the pre-main sequence stars. Now, they may look like stars in pictures, but there has to be a couple conditions that are met before they're actually considered main sequence stars. They have to get the fusion started. It has to be sustainable fusion for a long period of time. That's the life of the star. And then they have to attain that equilibrium. And once those two conditions are met, then we say that the birth stages are done and that the star becomes a main sequence star, right? And so the stages are all the same. If there's any differences, it's the amount of time that it takes for the stars. There is this inverse relationship between mass and time here, meaning that stars that form with a very large mass go through these stages very, very quickly. O stars and B stars will rip through this stuff in like under 1,000,000 years. Whereas stars that are much smaller in mass take a longer time, right? So do you remember how long it takes the sun to go through this process? Right? It was 30 million years. And the longest this process could possibly take would be around 100 million years, and those would be for the lowest mass stars. So that's kind of the summary of the birth of stars. So now we have our main sequence star, and what happens? What does it do? Well, not much. In fact, if we talk about a star as if it was a human life, it would kind of go like this. Fetus is created, conception occurs, and for maybe 4 months, we're going through these stages here, right? So 4 months is the incubation period, and then the human's born. There's no like childhood. You're merely an adult, and you kind of sit in a room and you just breathe, and the breathing is like fusion. You just don't really do anything. You just sit there and breathe, breathe and breathe. Maybe you got like a companion because you're part of a binary system, and you got another person that you can just sit in a room with and breathe. But you don't really do much, right? You don't interact with your neighbors. Yeah, you have some planets maybe that are orbiting you, but you don't really interact with them very much. And then, so if they say the person lives for 100 years, maybe the last year or two of their life, the breathing starts to become labored because you're running out of air, running out of fuel, and then eventually the object will transition to a giant star stage or a supergiant stage, and then boom, then they explode, just like a star explodes, and that's kind of really the life of a star. It's not exciting. As we saw earlier in this class, stars don't really interact much with neighbors. They are so far apart from neighbors, there's no real interaction that takes place. So it's mainly the life of a star is just the slow burn of the nuclear fuel until it's all gone. That's kind of it's all that happens there. So, all right, let's actually talk. I mean, there's not a lot to talk about, but let's talk about it. All right, so there's the two conditions for a star to be on the main sequence. They have to have that nuclear fusion in the core, and they have to have the hydrostatic equilibrium. And so a good way to think about these conditions is to understand stars or any objects that don't meet the conditions and why they don't meet the conditions. So we'll talk about condition 2 first, hydrostatic equilibrium. You're not a main sequence star if you don't have hydrostatic equilibrium. Examples of things that don't have hydrostatic equilibrium are giants and supergiants. Giants and supergiants are stars that are beginning to die, and it's because their fusion reactions have either slowed down or they get disrupted in some way. They kind of sputter, like kind of come on for a bit, turn off. And this is all just due to the fact that they run out of fuel. It's just like if you ever experienced running out of fuel in your car starts to do some funny things. It sputters and kind of doesn't have the same kick that it does. And same kind of thing happened in here. Now, for stars, though, that causes them to lose their equilibrium, right? So remember, think about the equilibrium, right? It's gravity pushing down and this gas pressure pushing back out. And that gas pressure is powered to a large extent by the fusion reactions. So if the fusion reactions start to stop or they slow down, you don't have that same energy there to push back against gravity. So the equilibrium gets broken. And interestingly enough, breaking that equilibrium actually causes the star to expand to a larger size. And we'll detail that in the next week when we talk about the death of stars. So we'll look as to why that exactly is happening. So those are examples of stars that are stars. Giants and supergiants are still stars. They have fusion, but they don't have their equilibrium anymore. Right? Examples of objects, I'm going to say objects, not stars here, that are not on the main sequence because of number 1. Those are brown dwarfs and white dwarfs. Now, we really haven't talked about either of these two objects here. And I'm going to talk about white dwarfs a bit more when we get to the death of stars. But real quickly, when a star like a giant star ends up finally dying, like there's no more fusion at all, the star does expand to a larger size and it starts to shed layers. And it will continue to shed layers until the core of that one star is revealed, and that is what we call the white dwarf. So these are things that look like stars in images. They shine, but they're not even stars. Not only are they not main sequence stars, they're not even stars. They don't have any fusion going on inside them. They do have equilibrium, though. That's interesting. There's a whole other process taking place there. That's for another time. But that's what a white dwarf is. So white dwarfs are not even stars, actually. Now, brown dwarfs are kind of a totally separate and really interesting thing. And then this is actually was my expertise. When I did my work in grad school to get my doctorate, I did my research in brown dwarfs. This was a really hot topic in the late 90s, early 2000s, and that when I was in college. So what are brown dwarfs? Well, turns out that there is a lower limit to the main sequence. You know that the smallest kind of stars you can have are M stars, right? Well, the question is it possible to have a mass that is so low that there really isn't enough of a match, the match that lights, everything up here? Is it possible that the mass of the object is simply too low to allow fusion to even begin in the first place? And it turns out that that is true. If an object is formed with a solar mass that is about 8% or 0.08 solar masses or less, then there is not going to be enough mass to get the core hot enough to start the fusion reactions. So these objects really never become stars, and we sometimes refer to them as failed stars. And they're not main sequence objects because they are not even stars to begin with. They never were stars. Again, you have to have about 0.8 solar masses. This puts you at around maybe 80 to 85 Jupiter masses. If you get that high in mass, then you can start the proton-proton chain. Under this mass, there are at least a couple fusion reactions you can do. You can fuse lithium, you can fuse deuterium, but these are not really sustainable fusion reactions because there's not enough fuel to sustain the fusion reaction. So there may be a brief energy source, but it's really not enough to call this object a full-fledged star. And I did my research, like I said, formerly this was in the early 2000s. And the reason why this was such a hot topic back then is because infrared technology had recently arrived at telescopes. Now, these objects are cooler than M-stars, and M-stars are already very difficult to find. So the brown dwarfs are even harder to find because they're cooler. So you really needed infrared telescopes and infrared detectors to detect their presence in the infrared, because they actually are brighter in the infrared due to their temperatures. Their Wien's law peak is in the infrared part of the spectrum. So we just started to discover a lot of these objects. Now, I believe it was in 1999 that they added a letter to the spectral sequence, and that's the L types. And then maybe about 3 or so years later, they added the T type, which is even cooler than the L dwarfs. And then a little while after that, I want to say maybe around 2009 or 10 is when they added what we believe is going to be the last letter, and that's the Y types. So, the classification sequence goes O, B, A, F, G, K, M. And then somewhere in the M and the L's is where you have the boundary between stars and brown dwarfs. A lot of brown dwarfs can be M's to begin with. And then because they don't have fusion reactions, they just kind of slowly cool off. And then they kind of transition into the L's and the T's and the Y's. So to some extent, the L, T, and Y's can represent like an age progression as these things just get cooler because they don't have a source of heat. They just kind of are initially get really hot and then just cool off over time. So somewhere in the M to L's is this boundary between what is a star and what is not a star. So we added these letters, right? So beyond M is L and T and Y. And then anything beyond Y would be basically traditional planets like Jupiter. Like a Y dwarf has a temperature of around maybe as high as 5,000 Kelvin, 4,000, 3,000 Kelvin. I mean, that's kind of like room temperatures, 3,000 Kelvin. Jupiter's cooler than that. I think Jupiter's maybe like 125 Kelvin, I want to say. Oh my goodness. So anyway. Now, the reason why I mention this is because there is, at least initially when this was first discovered, not a good distinction between what would be considered a free-floating planet. Like if we took Jupiter and we just toss it out of the solar system, right, would we call it a white dwarf? I mean, would it be considered a very cool white dwarf? And so for a while, we didn't really have a good distinction between what is a brown dwarf and what is a white dwarf. I mean, obviously, for a while, when these things were initially discovered, there wasn't really a good distinction what would be considered a brown dwarf and what would be considered a planet. Obviously, planets would be orbiting stars, right? But say we take Jupiter and we throw it out of the solar system, would we still call that a planet? Would it be a brown dwarf at that point? So it's kind of not really clear how we would do that. And so currently, the IAU, which is the International Astronomical Union, and this usually decides the definitions of things in astronomy, they are currently considering brown dwarfs to be above 13 Jupiter's masses. And the reason why that extinction exists is because if you're a 13 or above, you can probably do deuterium fusion, which is step 2 of the proton-proton chain, where you're fusing deuterium with another proton. And then if you're lower than that, you're probably a planet. So we're making a distinction here, not really that you're around a star. It's just that can you do deuterium fusion or not? So that means some brown dwarfs could be basically like a planet. It could actually be around a star, but it would be called a brown dwarf, and that means that we could throw Jupiter out and it would be called it'd still be called a planet, even though it doesn't orbit a star. So it's kind of weird. It's not a completely accepted idea just because you can't really look at an object and know how much mass it has right away. It's not an easy thing to determine. And usually when it comes to classifications or names for things, it's something that has to be very readily available to observe, and masses are not really easy to find. So anyway, this might change in the future, but this is how it stands at the moment here. So, all right, so life. What is life? For a star, it's this. So if you're a star, you're doing this at a minimum. It's the proton-proton chain. It's a 3-step process. You're taking atoms of hydrogen, you're smashing them together in a 3-step process. You're producing a lot of energy, neutrinos, and at the end of the 3 steps comes out a stable helium nucleus. And this is the life of a star. Every single star does this at a minimum. So you're familiar with this. We talked about this because our sun does this, like something like 98% of the fusion reactions in the sun is this. And because most stars are actually lower in mass than the sun, this is the primary source of energy that occurs in the universe. But you can do other things. Here are some of the other things that you can do. This next process is called the CNO cycle. Now, the CNO cycle is a different mechanism to produce the same thing that the proton-proton chain does. So like what is fed into this are hydrogen atoms. And what comes out of this is energy, neutrinos, and helium atoms. So if I would have put this material, these hydrogen atoms, inside of a box, and out of the other side of the box came out all the other stuff, if I didn't know what's going on inside the box, you would not really be able to tell if there's proton-proton chain happening or the CNO cycle happening. You have to open up the box and see what's going on inside. Now, the way this process works, and you know, this picture kind of looks a little wild here. There's a lot going on in this picture, so I don't really need you to know the details of the reaction here. I just want you to know the same thing I want you to know for proton-proton chain: what goes in, what comes out. The actual mechanism itself is kind of beyond the scope of what we want to study in this class, but I'll talk to you about it anyway. So you need a pre-existing carbon atom to be in the star, and it needs to be, you know, near the core where it has access to the nuclear fuel. So this does require some pre-existing carbon, and what happens is protons are added to carbon to slowly build up this carbon atom into different isotopes of carbon, nitrogen, and oxygen. That's why it's called the CNO cycle. And at the very end of the process, when the final proton is added to an isotope of nitrogen, then you can spit out a brand new helium nucleus, and then you can also produce the original carbon that was used to piece together this helium, and then that's recycled, and the process starts all over again. So this is just a different mechanism. It is a harder mechanism. You know, I mentioned that the sun does like proton-proton chain at like 98%. There is a small percentage of fusion reactions that actually is the CNO cycle in the sun. Typically, though, more massive stars do this in a greater amount. But let me ask you a question here. Like, why do you think this is harder to do? Think about this for a minute. In fact, as you think about it, there's kind of a better question to really think about first is, remember, why is the proton-proton chain even hard to do, right? The reason why the proton-proton chain is hard to do is because it's not very easy to take a proton and another proton and smash them together, right? They have this natural repulsion between them. And so they don't want to stay together. So you need enormous temperatures and densities and pressures to make sure that these things smash together. Okay, we call that the Coulomb barrier. Okay, what about the Coulomb barrier here? What are we trying to do? Trying to take a proton and smash it together with a carbon nucleus. That's 6 protons. That's a much larger Coulomb barrier than 1 in 1. This is 1 in 6. Now, carbon's a bigger target. It's a bit easier to hit a carbon atom, but you still got to overcome this 1 to 6 Coulomb barrier. So that's why it's really hard for the sun to do this, because you need temperatures that are even higher to get this to go. And the sun struggles to do this efficiently. More massive stars, like I say, can do this. All right. Now, some stars, we'll talk about the more massive stars here, or even stars that are on the way out, like stars like giants, they can get their core temperatures significantly higher. Like our sun is right 15 million Kelvin. Well, that will go up in the future as the fusion reactions start to shut down and gravity continues to crush the core of the sun. Those temperatures are going to rise. And for other stars, if they're more massive, their temperatures in their core can be really high. And if the temperatures are sufficiently high and that threshold is around 100 million Kelvin, you can start to dabble into some other fusion reactions. So one of those is called the triple alpha process. It's what you see in the diagram here. Now we're doing helium fusion. We're taking the helium atoms that exist inside of the star. And if, again, things are sufficiently hot, you can fuse 2 helium to make a gamma ray, a very high energy photon, and a beryllium atom. And then another helium can smash with the beryllium and create carbon. So this is called triple alpha process because a helium nucleus is known as an alpha particle. So you have 3 alpha particles that can create carbon. And very challenging to do, right? You need really high temperatures to do this, but this is one of the primary ways in which carbon has been produced in our universe. The vast majority of carbon that exists in the universe was made through this process here that exists inside of stars. Now, this process, I kind of like to think of this as like kind of like a gateway drug for stars. Like if you're dabbling into this, I don't know. You're treading into some dangerous waters here, because if you're hot enough to do this stuff, you can maybe take that carbon and do some other things. And so some of the most massive stars go a little crazy. And this picture here shows a variety of other types of fusion reactions that can occur. And this only really happens in the heaviest of stars. And they can create a lot of heavy element fusion reactions here. So you can see at the top here, there's a bunch of what are called helium capture reactions. So you can continually add helium to heavier and heavier things. You can make oxygen, you can make neon, magnesium. And then underneath is some really wild fusion reactions where you can take different carbon, nitrogen, oxygen elements, and you can create things that are heavier. Silicon, sulfur. And then the end of this is the end of the line, is the fusion of silicon to iron. Now, if you're doing this, it's a death sentence. If you're making iron, iron's a problem because iron is one of the most stable atomic nuclei. You can't fuse things with iron and make energy. You can't break iron apart and make energy. It's kind of, if you remember, there was this graph I showed you way back when we talked about fusion reactions, and it was a graph of binding energy with different mass numbers, and at the bottom of that graph was iron, and what that means is you just can't get anything out of iron. So if a star somehow goes really wild and because its mass is so high and it gets its temperature so high that it starts just going through all kinds of fusion reactions, if it goes through a process where it can make iron, it will cause the star to die. And die rather quickly, by the way. I mean, once a star starts to make iron, it's a matter of like a day where enough iron builds up that the equilibrium is broken so heavily inside the star just collapses on itself. The core is completely destroyed, and the amount of energy that's released from that is what causes the supernova explosions. It's the star literally exploding. And it's a very catastrophic death of a star. And there's not many stars that can do this. I mean, we're talking about stars that are 8 times the mass of the sun or higher. We're talking about O stars and B stars. Not an incredibly common thing, but something that stars can do if they are massive enough. So, all right. But anyway, regardless, it doesn't matter if you're a massive star or a lower mass star or whatever, all stars at some point run out of fuel. And that does spell the death of every star. Every star that exists today has a timer on it, and that says how much longer it's going to live, and that is based on how much available fuel it has. So if we want to talk about the HR diagram and what stars do, I mean, here it is. Here's our sun when it was first formed, and here's the present sun. And maybe at the very end of its life, it might get a little uptick in its luminosity. Maybe it's a little tiny bit, but it really doesn't move at all on the main sequence. It just stays there, doing equilibrium, doing the fusion, and at some point that starts to break down, and then we have the evolution to a giant stage. And that's all detailed in the next week of lectures. So, yeah, but if anything's interesting about this, I mean, you kind of want to know the time for this stuff. So here's our sun down here. Sun's G2, actually. So this number for the G0 is for a star that's maybe a slightly more massive star. And the G0 takes, 8 billion years to go through its main sequence life, where our sun is somewhere in the range of 9 to 10 billion years. Look at the massive stars, the O stars and the B stars. They are not only born rather quickly, but they rip through their fuel very, very, very fast. And they don't live very long. I mean, you can see here, the O star has like 1 million years of life. B star, tens of millions of years. That's pretty much it. A stars are about 500 million years of life. If you look down here at the bottom here, this is where it gets a little interesting. The K and the M stars. If you look at these numbers down here, like K0, that's the most massive K star you can have. And what's its years on the main sequence? 17 billion. Well, you may not know this, but I'll tell you now, our universe is 13.8 or so billion years old. So the life expectancy of a K star exceeds the age of the universe. What does that mean? It means that every single K star or M star that has ever been born in the history of the universe still exists to this day. And it's one of the reasons why there are so many of these stars, in addition to the fact that when star formation occurs, you tend to form these smaller clumps of matter. Both of those things contribute to having a very high population of low mass stars. But yeah, these stars, none of them have died so far. Some lower G stars are ones that have life expectancies around the age of the universe. So that's an interesting clue, and it'll become important when we talk about galaxies and understand how galaxies form and the life of a galaxy is, because these stars they persist. They last a long time. In fact, some of these M stars, you go down even lower. I mean, this is 56 billion. There are M stars that will live for trillions of years. Trillions, right? So, all right. Now, we're going to deviate here, seemingly. Right? That was the life of a star. That's all I got to say about it. There's not a lot. Not a lot that happens in the life of a star. So we're going to spend the rest of this time talking about a sort of adjacent topic to stellar birth, and that is birth of planets. As you might be aware, in the last 20 or so years, there's been a flood of what we call extrasolar planet discoveries. There's two terms that are used here. At least initially, they were referred to as extrasolar planets, but now we call them exoplanets because, I don't know, it sounds edgier or something. I don't even know why they do that, but I agree exoplanet sounds a little cooler, so let's go with exoplanet. So I kind of go back and forth even saying like extra, because I was going through school, we always call them extrasolar planets. We weren't edgy back then, now we're edgy. So exoplanets is now the name we're going to give here. So because it's tied so closely to stellar birth, we're going to be discussing that now. But there's been an enormous number of discoveries. So many discoveries now that we now have a better understanding of not only how planets form, but we have a better understanding of the different types of planets that can exist. And of course, all of this is leading to what is potentially the most exciting discovery in all of astronomy that will hopefully happen someday is the discovery of another Earth. Whether that is a planet that is habitable by people, or whether it's just a planet, or even a planet that actually has, extraterrestrial life on it. So that's obviously the kind of the one of the more exciting outcomes that can happen from this study, right? All right, let's just go back through our solar nebula theory, because if we're trying to understand the formation of planets, because it's tied to the formation of stars, we kind of have to see like what part in the formation of stars do these planets come about, right? So the idea with the solar nebula theory is you start off with some kind of, large cloud of gas that something triggers it to collapse, right? So let's just consider that, based on the discussions we previously have, this is like a little chunk that came off of one of these, these interstellar clouds, and this chunk is about to form, a new star for ourselves. So it's shrinking in size. It starts to spin more rapidly, so it flattens out into a disk, and then the vast majority of the material will spiral into the center and form the star. Like it's going to be like 99% of the material, but some material remains out in the disk. And as this entire disk starts to eventually cool, we are going to see clumps of matter start to appear. And as an object starts to go around, it's going to also do accretion. As it sweeps around the disk of this newly formed solar system, it's going to start to gather up material from its surroundings. And the picture that you see down here is kind of the stuff we're looking for. We imagine that we would start to see rings of material form, indicating that there's objects going around sweeping up material. So the gaps are all material that's been pulled into the orbit of these stars and orbit of these planets. We actually may start to see clumps of matter in these things. So this is what we're looking for to confirm our ideas of how planets form. Because we didn't always believe this, right? I mean, prior to this, we had some pretty wild ideas of how planets form, but now they're tied to solar nebula theory. So we need to study young stars and look for evidence of planetary formation. That's what we're trying to do here. All right, so let's look at the evidence. One of the best places to look for this stuff is the Orion Nebula. The Orion Nebula is a nebula that is somewhat nearby to the solar system, and it contains some of the youngest stars that we could possibly study. So it's a good combination of being nearby, so we can see a lot of detail in our images, and being pretty young. What does pretty young mean? Most of the stars in the Orion Nebula, we believe, are between 1 to 5 million years old. So there should be lots and lots of examples of star formation occurring, and therefore planetary formation going along with the star formation. So in this particular part of the Orion Nebula, we do see a lot of, these block globules, right? These clumps of matter that are condensing down. And many of these globules, when they become more advanced, start to develop disks on them. So we see a disk here. And you see a little light source above this disk. That's the light of this new star. It's starting to peek out from behind the disk there. So we definitely see a lot of the flattening that are supposed to occur in these globules that show the disks that are forming. Hubble made some really amazing discoveries when it was early on in its history, because it looked at T Tauri stars. Remember, T Tauri stars are pre-main sequence stars. These are really young stars. And the idea was that if you looked at a sufficient number of these young stars, you should see what are called dust lanes, or the presence of dusty disks around them. So the one on the bottom right is a really great picture of this, where we can clearly see there's this dark bar that goes through the center of this star. We are seeing a disk edge on. We're seeing the edge of the disk, and the other objects here, we're also seeing edges of disks. They're slightly inclined to our solar system. So like in the ones on the top here, we see the bottom is a little bit more brighter because the disk is kind of tilted up a little bit. So we see the bottom part of the star there. But, Hubble discovered that disks around stars were incredibly common for young stars. So that supported the idea of, stars and planets forming together as part of the solar nebula theory. So that was really good evidence of that. Of course, now you have to start looking at these disks in more detail. and say, okay, well, if there's disks that exist there, let's try to see more detail in the disks and let's start looking for these features. Are there rings? Are there clumps that we are seeing here? Is the disks warped in any sort of way that maybe reveals the presence of something that is traveling in the disk? So, based on the solar nebula theory, we would expect virtually all stars to have some kind of solar system to it. In fact, we are discovering that for the vast majority of stars that we look at, we do find solar systems. So, again, more support for solar nebula theory. And again, we initially refer to these objects as extrasolar planets. This means planets discovered outside of our solar system. And so the pictures that you see here are some of the more recent pieces of evidence for finding material around stars that are going to form planets. We call this protoplanetary material. Now, these are very special images. They are called coronagraphic images. Now, a coronagraphic image is an image of a star that intentionally blocks out the center of the image. So we actually have a technique in the telescope. It's a particular mask that's put onto the telescope to prevent us from seeing the star itself. Because the stars are bright, right? They're going to outshine everything around it. So the idea is that we block out the light from the center star, and that's going to allow us to see the stuff that's around the star in a much more easier fashion, right? An analogy I could give you is, imagine you're at some kind of like sports stadium and you have these huge floodlights above you that shine onto the field, and you look at the lights and they're really bright and you can't really see much because the light is kind of so intense. But then you put your hand up to the light, and then to your horror, you see like a swarm of like moths going crazy around that light. You couldn't see that when you didn't block the light because the light outshines all the moths. But then you block the light and there you go, there's all those moths. So it's kind of like that. It's kind of like that, where because you can block out the center light, it's going to be much easier to see the things that are around it. Right? And these pictures show some pretty amazing things. I kind of selected a few of the highlights. So in particular, we see this one at the top here. It's called Beta Pictoris. We see that the disk is not totally uniform, that it contains warps and potentially rings, because we're seeing an edge on. So areas that are a little thicker in the disk probably is a ring structure. We definitely see a ring on the one on the left here. So again, rings are going to be formed because you have objects going around sweeping up material. That causes the ring to form. The one at the bottom here, we actually see clumps of matter in the disk. These are probably future planets. So we have enough observations now that we are very confident. And in fact, the solar nebula was originally called the hypothesis, and it's recently become a theory. I say recently, but 20 years ago or so, because we've solidified enough observations. So we solidified the theory with enough observations. Stars and planets form together, and the planets form out of the disks of these stars. So that's very evident to us. All right, now, great, we see evidence of this stuff. So obviously the next step is, okay, let's look at stars that are a little bit older, and let's start finding planets. Well, that's hard to do. We have discovered, oh gosh, I'm recording this in October 2023, and I want to say over 5,000 planets have been discovered outside the solar system, with another maybe like 10,000 yet to be confirmed, but probably very likely. To date, 20 stars, 20 planets have been discovered by directly viewing them in external solar systems. It's just extremely difficult to do. Here is one example where we did do this. So the first thing would be a direct detection of an extrasolar planet. And like I said, we have thousands at the moment known, and there's like about only 20 discovered through a direct detection. So this is a star called Fomalhaut, and it also has a coronagraphic mask on it. It's taken with the Hubble Space Telescope. And so we block out the center light from the star, and we do see that there is a disk that surrounds the star, and we do see a nice ring of dust, definitely indicating something going around, producing this ring. Fomalhaut is a somewhat young star, not super young like the examples we saw, but something that's a little bit older. And we looked at this because we thought it would be very likely they would see this any planets that exist here. Now, the reason why we might see planets here is the following. Now, normally, planets are not seen around stars directly. It's because stars are so insanely bright, like billions of times brighter than a planet, that the planets get lost in the light of the star. Planets don't produce their own light, mostly. They reflect light, right? But Fomalhaut is a special situation where it's a star that's somewhat close to us. So any planets that exist would be more noticeable because the angular size between the star and the planet would be larger. Because it's a young system, the planet may actually be producing some of its own light because it's initially very, very hot. So it's possible that in systems like these, you would be able to spot stuff. So they did notice there are some star-like objects discovered near the disk. And what they did is they continued to take pictures of this region, looking for how these stars or potential planets move. This Fomalhaut is not really an object that's close enough that parallax would work here, but it is close enough that something called space motion can be used to detect a member of the system. Now, space motion doesn't tell you the distance to something, but it does tell you if two objects are close enough together that they are associated with each other gravitationally. And the idea is basically this: like, we may not know the distance to Fomalhaut, but if something were to be next to Fomalhaut, they would move collectively in the same manner as they move in the galaxy. So this object down here in the bottom left is called a Baccarat star because it did not move over the course of a couple of years the way Fomalhaut moved, but this object on the right here did. And they're showing this line here, and that's the expected space motion of an object that is part of the Fomalhaut system. And there it is. Look at that. That's a planet. That's the planet. I'm sorry, it's not exciting. I mean, it's cool to see that. It's a bright pixel surrounded by 8 fainter pixels. I'm sorry, that's as good as it's going to get. Direct detection is exciting in some ways, but we're not seeing pictures like we see for the planets in our solar system. These things are too far away. These things are just a little blip, a little tiny dot on an image. And unfortunately, in our lifetimes, we will not see a planet outside of our solar system in the same way we see the planets in our solar system. It's just not happening. So cool to see this. Although not the most exciting image to see. I mean, if you're an astronomer, you're like, oh my gosh, this is amazing. But the average person's like, so what? It's just a little pixel there. So anyway, my point is that direct detections are not the way to go. We have not discovered stars in this manner at all. So how do we detect them? Well, there are a couple major indirect detection of planets. And the first one of these is called the Doppler method, or also called the wobble method. I think wobble is probably the more common term these days for this method. It's an indirect extrasolar planet detection method. So we don't see the planet directly, but we see the influence that the planet has on its parent star, and that reveals the presence of the planet. So that's why it's called an indirect detection, because while we don't see it itself, we see its effects. And this is sort of the more traditional method, meaning that this was when planets were originally discovered. They were primarily discovered through this particular method here, right? So what's happening here? Well, the animation on the top here is kind of showing what's happening. If you have a planet that is sufficiently massive and sufficiently close to its star, it's going to have a gravitational influence on the star. And from our perspective, the star is going to appear to wobble in the solar system. There is so much mass in this planet, and it's so close that the center of mass of this solar system is not the center of the star. It's on like the edge of the star, and so it causes the planet to kind of wobble. It causes the star to kind of wobble. And the picture on the bottom left here is how we see things from Earth. Now, we may not see the exoplanet in orbit, but we do see this star wobbling. And half the time, the light from this star is going to be blue shifted towards us, and the other half of the time, it's going to be red shifted. Okay, because from our line of sight, the planet's either going to be moving towards us or away from us as it's being wobbled around. And so we can create graphs like this on the bottom right here. Now, this is a very famous piece of data. This 51 Pegasi was the very first time we discovered a planet around another star. It's like 95, I want to say. And we see that 51 Pegasi, that star, is experiencing these periodic Doppler shifts. It's going back and forth, back and forth, back and forth, because there's some star that is pulling on this thing. And so through this data is when we first discovered the existence of other planets. This method to date, again, this is like fall of 2023, we're at about 1,000 planets discovered through this technique here. Now, this technique is great, but it has massive limitations, and it inherently has a ton of bias in the method. And here's the bias. This is based on gravity, right? So this will show the most dramatic effects if you have really massive planets very close into their stars. Very close into their stars. So in fact, the first few planets that were discovered in this method were a class of planets that we didn't even know existed. And we call them hot Jupiters. These are planets that can be the size of Jupiter or larger, but they are closer to their parent star than Mercury is. So this was totally a shock to us. But this Doppler method, it kind of, like I said, creates a bias. These objects are going to have the greatest gravitational influence on their stars, so they're going to be more obvious to see. And that's what we're seeing here. We're seeing the few that exist. Not many of these exist, but the few that do exist, they really stand out in this method here. And this was a real puzzle to us because this kind of goes against our normal ideas of how solar systems form. Like, we shouldn't have Jupiter-sized planets so close into their stars. So it was a bit of a puzzle at first. We believe now that we are catching planets in the process of a migration. So it's very likely that these hot Jupiters were not hot to begin with. They actually existed far out in their solar systems, and something caused them to get pushed closer to their parent star. And they won't stay this way. Over time, the intense energy from the star will boil away their gases, and they'll turn into something much smaller later on. But this is some of the objects we find. Now, this method, because it biases larger planets, it's very difficult to find Earth-like planets in this method here, because like in our solar system, if an alien civilization was trying to do this in our solar system, they would definitely see Jupiter and Saturn, but it would be very difficult to detect Earth because the Jupiter and Saturn effects are going to be so much more, significant than a small planet like a terrestrial planet. So this method is not really good for finding Earth-like planets. But we have another indirect detection method, and the vast majority of planets are discovered with this method here. It's called the transit method, and it relies on an eclipse to take place. So the idea behind this is we look at a star, and we have to initially hope that the star has a solar system that's aligned in such a way that when the planets orbit the star, they will regularly eclipse the star. And we will see that because as the planet orbits, periodically the light that comes from the star will dip. And that's what's shown in the animation here, the dip of what we call the light curve. So as the planet gets in front of the star, the amount of light that we get from the star goes down because it's being blocked by the planet. And this is a good technique because it's something that happens on a planet-by-planet basis. So if there are Jupiters and Saturns, obviously they're going to block a lot of light, but they'll move out of the way. And when a terrestrial planet gets in front, we'll separately see those effects. So we have discovered a lot of terrestrial planets like this, and I'll show you some examples in a moment here. But there's obviously a limitation to this method. I mean, you do need to have a solar system aligned properly to see this. Most of these are discovered with a mission called the Kepler Space Science Mission. It was a mission that was put up, and it stared at a field of like 1 million stars, and it just watched them. just watched them, and looked for these dips. And, most of those stars aren't going to have solar systems that behave in the way we want to, but like tens of thousands do. And so we were able to get a very large number of detections through Kepler. And in fact, later in the lecture, I'm going to refer you to a video you can watch that talks about some of the interesting Kepler discoveries. So, but yeah, this is the other method that has been used. And anyway, let's look at some of the more important discoveries here. One of the first discoveries that Kepler made is called Kepler 186. And Kepler 186 discovered a system of planets, actually, 5. Now, most of these planets that were discovered very close into the parent star. Now, Kepler 186 is a star that is less massive than the sun, and the green shaded region that you see here is what's referred to as the Goldilocks zone or the habitable zone. This is a region around the star where the temperatures are moderate, and moderate meaning temperatures that are similar to Earth-like temperatures, and temperatures where if water exists, it would be in liquid form. So as you can see, most of the planets in the system were too close in, but they did find one that's kind of on the outer edge of the Goldilocks zone here, and you can see it has a size very similar to the Earth. We believe it's a bit more massive than the Earth, though. So its surface gravity would be a little bit larger, but it's very cold. The average temperature, minus 120 Fahrenheit. So there may be regions where it's warm enough for some liquid water to exist, but it would be harsh, right? This is a very harsh environment here. But it was very important to see a discovery like this because it did resemble the Earth to some extent. Later on, Kepler discovered an object called, it's 452b. 452 is the star. The star is really similar to our star, actually. It has a very similar Goldilocks zone around it. And there was a planet discovered that was just outside of what the Earth's orbit would be, so just beyond 1 AU. So in terms of placement, it's right where it needs to be. However, we did discover this object is a bit larger in size and in mass. Turns out the surface gravity is a little more than double what it is on Earth. So if you were to be at this planet, you would feel twice as heavy. That's kind of unpleasant. It is a bit warmer, though. Average temperature is around 17 Fahrenheit, where Earth is like, I think average temperature at Earth is something like 58, 59 Fahrenheit. So kind of cold, but there are plenty of places on Earth that have an average temperature like this. So now this next one wasn't a Kepler discovery, but it is a really, really, really fascinating discovery, and it's something that revealed to us a whole system of terrestrial-like planets. It's called the TRAPPIST-1 system. TRAPPIST is the name of the telescope facility that, I think it's a telescope facility or a telescope project that discovered this system. And it's somewhat nearby. A lot of the Kepler discoveries are very far away, like 1,000 light years away or something like that. But this is 40 light years away. So it's that's kind of close. I mean, like maybe not like in our lifetime we can go here and check it out, but definitely a feasible project in the future for the future of humanity if we ever make it that far. But anyway, so you can see here the TRAPPIST system is a very different type of star, though. It's as you can see here, there's kind of showing you that the inner solar system of our solar system is where all this stuff would be contained. The star is a low mass star, very low mass. It's like an M8, I think. Very, very low mass star. So it's not like the sun, and so its Goldilocks zone is really close to the star itself. They discovered 7 terrestrial planets in the system. 7 terrestrial planets that technically lie somewhere in this habitable zone. And I think the F planet is the one that's most like the Earth, just in terms of location, temperature, size, density, all that stuff. So, we'll look into these more in the future, but these are really interesting. I mean, it's a whole solar system that we discovered here. There's some issues with habitability, though. Some planets are tidally locked, meaning one side is always facing its star, the other side's in total darkness. That's going to be a weird system. Some of these may have so much water on them that the entire surface is just water world. There's no land on some of these things, so that's interesting. And there's a big problem with being this close to the star. Now, this may be the Goldilocks zone. This may be the region where liquid water would exist, but if you're this close into the star, you are going to be more subject to like flares and harmful radiation that comes from the star. So that's going to be really challenging for life to develop on these things because, you just constantly have the solar radiation hitting your atmosphere or your surface, and it's going to make life very difficult to develop. So, all right. Anyway, just to finish this up here, this was a bunch of statistics put together about all the exoplanets that were known at the time. This graph that you see here is about 5 years old at the time of this recording. And at the time this was released, if you see in the middle here where it's boxed, 55 Earth-like planets were known at the time. Now, since this was created, the number has reached about 200. So these are 200 candidates that are going to require follow-up observations. They have all of the ingredients for life to be present on them. Like it has the right distances and therefore the right temperatures from the star. It has likely liquid water on the surface. So we're going to do follow-ups for these. And you'll hear about this in the next 5, 10, 20 years. And it's very likely one of these objects will show up with clear signs of liquid water, maybe signs of oxygen in the atmosphere, indicating the presence of life, or we may actually just find signals of life here. So it's a really exciting time to be seeing this stuff because, like I said, there's a very good chance in the next decade or two that one of these things are going to turn out to be an Earth-like planet, and that's going to be a huge change in astronomy. Like it's really going to be a big paradigm shift in how we focus our work, I think, personally. So, all right, that's the end of this.